Greetings and salutations, magical chemists! Today we're going to learn how to balance redox reactions using what's known as the half reaction method. In this method, the reaction is going to be broken down into two half reactions, one for oxidation and another for reduction. Each half reaction will include electrons, and it will be balanced for its charge. Finally, the two half reactions are multiplied as necessary, so electrons lost and gained will be equal when those half reactions are combined. Luckily, there's a 4-step process you can use to ace redox balancing. It's called the ACE technique. Now, the first step is to write the half reactions for oxidation and reduction, but without electrons. Next, you'll use the following 4 steps to balance the reaction. You'll start by balancing atoms. Next, you'll balance the charge with electrons. And then you're going to equalize the number of electrons by multiplying as needed, so both half reactions have the same number of electrons exchanged. Finally, you'll add the two half reactions together, canceling anything that appears on both sides. And you'll notice the order of the steps spells, well, kind of, aced. Atoms, charge, equalize, and, add. Almost. All right, let's take a look at what this technique looks like in practice. We're going to start with a simple example and then move to a more complicated one. All right, before we can do anything else, we have to start by separating our complete reaction into half reactions. Well, that's actually going to be really straightforward because you're going to isolate things that have the same atom. So copper 2+ is going to go to copper. That's one half reaction. And solid sodium goes to a sodium ion. That's your other half reaction. You've probably noticed that I'm not writing states of matter. However, it is essential to add in the states of matter at the very end when you're done. It just saves some time if you're not writing it all along the way as you go. Okay, so we've got our two half reactions. Notice I actually didn't identify which was oxidized or reduced because it doesn't matter. You don't have to spend the time figuring it out to be able to use this technique effectively. So let's start our ACE technique by balancing atoms first. Well, you might be thinking, Lestic, it's already balanced. There's one copper on each side for that half reaction. There's one sodium on each side. Perfect. We don't even need to use the letter A for atoms. They're already balanced. And a lot of times that will be true, but not always. Okay, now we need to balance the charge, and the charge is definitely not balanced on each half reaction. Here's how you can tell. If we look at the copper half reaction, the reactant side overall has a +2 charge. The product side has a charge of 0. That does not add up. Luckily, there's an easy way to fix it. Add electrons. Since the only way we can fix the charge is by adding electrons, which are negative, you're basically always going to add electrons to the side that is too positive or not negative enough. In this case, that means we have to add electrons to the reactant side. How many? Well, got to get rid of 2 positives. I need 2 negatives. If I add 2 electrons to the reactant side, let's double check that charge balance. Now on the reactant side, 2 positives and 2 negatives add up to 0, which is exactly equal to the charge of 0 on the other side. Boom. You're done with this half reaction for charge balancing. Now let's balance the other half reaction. For the sodium half reaction, this time the reactant side is equal to 0, and the product side is equal to +1, which of course is not equal. That means we need to add an electron to the more positive side to balance this out. Now this half reaction is balanced for charge. Perfect. Okay, we've balanced atoms. Kind of, they were already balanced. We've balanced charge with our electrons, and now our next step is to equalize. Notice the number of electrons gained by copper is 2, but the number of electrons lost by sodium is only 1. They are not equal. Well, that's okay. We're just going to double the sodium side. Since each sodium atom releases 1 electron, if you have 2 sodium atoms, you will thus produce 2 electrons, which is exactly the same number of electrons that copper 2+ needs. All right, our last step is to add these 2 half reactions together. When adding up 2 reactions together, it's important to realize that you can cancel out anything that's the same on both sides. And hey, There's 2 electrons on the reactant side. There's 2 electrons on the product side. They are dead to us. You can cancel them out. If you have correctly balanced your half reactions, the electrons will always cancel when you are combining them to get your complete balanced equation. Oops, I just realized I forgot the 2+ on that original copper. Sorry about that, so please make sure you make that edit in your notes. All right, now we can combine our reactions. After adding the 2 half reactions together, make sure you remember to add in your states of matter. And now you're done. I just made a note to make sure that you are recognizing this point, that electrons should always cancel out when you add up your reactions, your 2 half reactions, which means electrons will not show up in your final equation. All right, let's go ahead and try a slightly more complicated example. Although this equation is a tiny bit more complicated, we're going to use the same strategy. First, we're going to isolate into half reactions. And remember, you're going to do that by just finding atoms that are the same on both sides. Going to our ACE technique, the first thing we do is balance atoms. And hey, we actually need that in the oxygen half reaction because there are 2 oxygens on the reactant side, but only 1 on the product side. Of course, that's an easy fix. And the aluminum half reaction is already balanced for atoms. Now we need to balance charge. Watch out that multiplicative coefficient multiplies the charge. So you have to take that into account. Technically, there is a -4 charge on the product side of the oxygen half reaction, but a 0 on the reactant side. Remember, we can only balance with electrons. So I think you should try. How many electrons do we need to add and where? Go ahead and fill in the number of electrons needed. And when you're ready to check, unpause the video. If you added 4 electrons to the reactant side, you win. All right, I would like you to try the same thing on the aluminum half reaction. Where do those pesky electrons go? Again, pause the video and unpause when you're ready to check. This time, electrons needed to be added to the product side to cancel out the 3 positive charges, right? If a solid aluminum goes to aluminum 3+, it's because it gave away 3 electrons. Notice 1 half reaction will always have electrons as a reactant because something's being reduced. The other one will always have electrons as a product because it's being oxidized. It always has to go one on, basically electrons have to be gained and lost. It just doesn't matter which side you're writing each half reaction. Okay, so now we've balanced the atoms, we've balanced the charge, we need to equalize our electrons. 4 gained, 3 lost. Well, in this case, hopefully you recognize the only way to get the equalize the electron transferred is we've got to multiply up to 12. That means multiplying the oxygen half reaction by 3 and the aluminum half reaction by 4. I honestly don't usually rewrite them after I've multiplied like I did in the first example, but what I will do is I'll rewrite the multiplied ones when I'm adding them together. So if you are feeling brave, you should totally try to add these up and see what the final reaction is. If you are not quite feeling that brave, go ahead and continue watching the video, but otherwise pause and unpause when you're ready to check. All right, when you're rewriting these 2 equations and getting ready to combine them, hopefully you noticed that just as planned, the number of electrons are equal on both sides and thus cancel, right? The number of electrons gained by oxygen has to equal the number of electrons lost by aluminum. You can't mysteriously make up or lose electrons. And then you finish your combining the 2 half reactions, and that'll give you your final equation. And of course, you totally remembered to put in your states of matter when you wrote your final combined and balanced reaction. As you get faster in this process, you may realize that you need to write down fewer and fewer steps. And shockingly, that's okay. Balancing redox reactions is still balancing reactions. And even in free response, you are not required to show work for balancing reactions. Well, I hope that was some good news to end the video. And there you have it. Thank you for playing with the glories of chemistry.